Good evening, my dear students and my dear parents. Welcome to ACE Engineering College YouTube live session. Why I am doing this video? Because this video will be useful for the students who are going to write exam in the external exam. Today we are going to discuss chapter 5, unit 5 of applied physics. Chapter 5, it consists of two parts, that is lasers and optical fibers or fiber optics. Fiber optics. My topic today is fiber optics. In this fiber optics, what we are going to learn? The important topics in fiber optics are structure of an optical fiber. So we are going to discuss what is the structure of an optical fiber. An optical fiber, okay, it has lot of applications. We are going to discuss that applications the last. Okay, and what is the principle involved in the working of an optical fiber? What principle is involved in the working of an optical fiber? The third one is acceptance angle and numerical aperture. Acceptance angle and numerical aperture. This topic is very important, and this derivation is very important. Okay, you will get repeated question, this one. The next one is the problems related to acceptance angle and numerical aperture. So in the examination paper you will also get some problems. So we are going to solve some of the problems in this discussion. The last one is attenuation in optical fibers. What is this attenuation? Attenuation is nothing but losses, energy losses. While the signal is transmitting through the optical fiber, there may be some losses in optical fibers. That loss is known as attenuation. So today we are going to discuss about the attenuation also. So let us start our first topic, that is structure of an optical fiber. So structure of an optical fiber. If you see, an optical fiber looks like this. This is the diagram of an optical fiber. Optical fiber mainly consists of 5 parts. They are, you can see this. This is called core. The inner part one is called core. This core is surrounded by cladding. This core and cladding are again surrounded by a coating. After that, so this structure of an optical fiber, it consists of mainly 5 parts. The inner part is known as core. This core is surrounded by cladding. You can see in this picture. This core and cladding are surrounded by a coating. You can see here coating. And this coating is surrounded by strength membrane. Strength you can see the strength member. All these inner parts are surrounded by outer jacket. These are the important parts of any optical fiber. If we come to this core medium or core, this core is made up of a special type of glass material, that is silicon dioxide. Silicon dioxide. This core is made up of a glass material which is silicon dioxide. What is the thickness of this core? The core thickness is, it is around 10 to 50 micrometer. It is around 10 to 50 micrometer. And what about this cladding? The cladding is also made up of a special type of glass material, that is silicon dioxide only. Both core and cladding are made up of silicon dioxide. But what about the diameter of this cladding? The diameter of this cladding is around 125 to 200 micrometer. It is around 125 to 200 micrometer. So core and cladding are made up of same glass material. But what is the difference between core and cladding? The difference between core and cladding are refractive indices. The refractive index of cladding is slightly lower than that of core. That means the core has higher refractive index compared to cladding. So how to make the refractive index cladding to be lower than that of core? That means by adding some of the impurities like boron, phosphorus, germanium. Okay, if you add such type of impurities to the cladding material, okay, you can make the refractive index of cladding to be slightly lower than that of core. Okay, but what about the strength member? The next part is a strength member. Strength member, it is made up of a special type of material called Kevlar material. A special type of material called as Kevlar material. This strength member, Kevlar material, it mainly gives strength to the fiber. Mainly, okay, it gives strength to the fiber. It gives the tensile strength to the fiber. Okay, that is the use of this strength membrane. The last part is outer jacket. What is the use of this outer jacket? Outer jacket, it is made up of black polystyrene. It is made up of black polystyrene. It mainly, okay, it protects the fiber from outside damages. It protects the fiber from outside damages. Suppose if you bend the fiber, or okay, if you bend the fiber, if you stretch the fiber, if you roll the fiber, optical fiber, what happens? There may be some damages. In order to protect the optical fiber from such damages, this outer jacket is used. It is made up of black polystyrene. Okay, so this is the structure of an optical fiber. Once again I repeat, optical fiber consists of 5 important parts. They are, the inner part is called core. Core is surrounded by cladding. Cladding and core are surrounded by strength member. And the last part, the outer part is called outer jacket. Core and cladding, they are made up of same type of glass material, that is silicon dioxide, but the only difference between them is their thickness and also the refractive indices. The refractive index of core is slightly greater than that of refractive index of cladding. Okay, and also I told you how to make the refractive index cladding to be lower than that of core. Okay, by adding some impurities like boron, phosphorus, germanium, okay, to the cladding material, you can make the refractive index to be lower than that of core. And a strength member, okay, it is made up of a special type of material called as Kevlar material. It mainly gives strength to the fiber. So Kevlar material is the strong material. Okay, so it gives strength to the fiber. The last one is outer jacket. It is made up of a polystyrene material. It protects the fiber from the outside damages. If you stretch or roll or bend, okay, those damages, you can protect the fiber from outside damages. The next one is, the next topic is principle in the optical fiber. So what is the principle involved in the working of an optical fiber? You can see the principle involved in the working of an optical fiber is total internal reflection. This total internal reflection. Okay. So what is this total internal reflection? So I am going to discuss about this total internal reflection. Okay. So what is this total? Before this total internal reflection, I would like to tell you what is refractive index. Any medium will have a refractive index. Okay. The refractive index is denoted by N. N is equal to C by V. N is equal to C by V. What is a C? Speed of light in vacuum. Speed of light in vacuum by speed of light in medium. Okay, this is refractive index. Refractive index is equal to speed of light in vacuum by speed of light in medium. Okay, you can see that the refractive index is inversely proportional to speed. What is the relation between refractive index and speed? As as speed increases, refractive index is decreasing. Okay, if the speed of a light in a medium is more, the refractive index of that medium is less. Okay, so depending upon this velocity or speed, okay, if the speed of light is more or speed of light is less, we have two types of mediums. We have two types of mediums. What are they? What are the two types of mediums? I consider this is one medium, let it be air medium. Glass medium. So when the light ray is traveling from this air to glass, what happens? Instead of going in its original direction, its speed, its direction changes. Why direction of the light ray changes? Because the speed changes. Okay, when the light ray is going from air medium to glass medium, instead of going in the original direction, because of the change in the speed, what happens? Its direction gets changed. Okay, and we can observe that the refractive index of air, is around 1.003, approximately we can take it as 1. Okay. What about the refractive index of glass? It is around 1.50. When you compare air and glass, okay, the refractive index of air is 1, the refractive index of glass is 1.5. So since glass has more refractive index, automatically the speed of the light ray decreases. So when the light ray is going from air to glass medium, what happens to the speed of the light ray? It reduces. The speed reduces. It slows down, I can say. Okay. So when the light ray is going from air to glass, the speed decreases. So we will call this air as rarer medium. Now air medium is known as rarer medium and this glass medium is known as denser medium. Okay, so there are two types of mediums, air medium and glass medium. Air medium is known as rarer medium. Why air is known as rarer medium? Because its refractive index is less as compared to glass. When you compare the air medium with glass medium, the refractive index of air is less. That's why we call it as rarer medium. And automatically the glass has higher refractive index as compared to air. We will call it as denser medium. Denser medium. Okay. So there are two types of mediums, rarer medium and denser medium. Rarer medium and denser medium. Now I consider a situation where the light ray is going from denser to rarer. Denser to rarer. This angle, let it be I. This is called angle of incidence. Angle of incidence. What happens when light ray is going from denser to rarer? Okay. We can observe that this light ray, okay, there are three possibilities. There are three possibilities for that light ray, depending upon this angle of incidence. Okay. Now I consider a case where this light ray, it is traveling along the interface after refraction. That means the light ray will not enter into rarer medium. The light ray will travel along the interface. That means the angle of refraction is 90 degrees. What is the angle of refraction? Angle of refraction is 90 degrees. Okay. Now you call this angle of incidence is called as critical angle. What is this angle of incidence known as? Critical angle. So how can you define critical angle? Critical angle is defined as the angle of incidence for which the angle of refraction is 90 degrees. The angle of incidence for which the angle of refraction is 90 degrees. That angle of incidence, we are calling it as critical angle. Critical angle. Okay. Now I consider a case, another situation where the light ray is traveling with an angle of incidence less than critical angle. I consider a case, okay, where the light ray is traveling, again it is traveling from denser to rarer only. Denser to rarer, but the only difference is what? The angle of incidence is less than critical angle. Then what happens? This light ray undergoes refraction. That light ray will enter into rarer medium like this. Actually its original direction, let it be like this, but since it is entering into rarer medium, okay, it suffers some deviation. So it undergoes deviation. This is refraction. Okay. So when angle of incidence is less than critical angle, what happens? It undergoes refraction. Okay. Now I consider a situation where angle of incidence is greater than critical angle. Angle of incidence is greater than critical angle. Again, the light ray is going from denser medium to rarer medium. Denser to rarer. The light ray is going from denser medium to rarer medium, and angle of incidence is greater than critical angle. Then what happens? What happens to the light ray? The light ray, it will not enter into a rarer medium. It gets totally reflected back. It gets totally reflected back into the denser medium itself. It gets totally reflected back into the denser medium itself. This phenomenon is known as total internal reflection. This phenomenon is known as total internal reflection. Now what is total internal reflection? When the light ray is going from denser medium to rarer medium, okay, when the angle of incidence is greater than critical angle, the light ray gets totally reflected back into the denser medium itself. This phenomenon is known as total internal reflection. So, okay, this is the main principle involved in the working of this optical fiber. How this total internal reflection is applicable, how this total internal reflection is seen in optical fiber. Let us see how this total internal reflection. Suppose this is core medium. I consider this is core medium. An imaginary axis passing through this core medium, we will call it as fiber axis. Fiber axis. Core is surrounded by cladding like this. This is cladding. Okay. Now, what happens here? This is core. This is cladding. This is fiber axis. Okay. When the light ray, okay, when the light ray, it is launched from air medium. When the light ray is launched from air medium, what happens here? The light ray, it is trying to go from core to cladding. As we already know that the refractive index of core is slightly greater than the refractive index of cladding. That means core is acting as denser medium, cladding is acting as rarer medium. Core is acting as denser medium, cladding is acting as rarer medium. Now the light is going from which medium to which medium? Denser medium to rarer medium. That means core to cladding. Okay. Now if you can make this angle greater than critical angle, if you can make that incident angle greater than critical angle, then what happens? This light ray will not enter into the cladding medium. The light ray gets totally reflected back like this. The light ray gets totally reflected back, okay. Okay. Sorry for the disturbance. So, when the light ray is trying to go, again I will draw, this is core medium, I will consider this is core medium, and this is cladding, this is N1, this cladding is N2, okay. This is fiber axis. Okay. When the light ray, it is going from air medium to core medium. Now from here onwards, the light ray is going from core to cladding. Core to cladding. So I already told you, core will act as denser medium. Cladding will act as rarer medium. Okay. So when it is going from denser to rarer, this angle becomes crucial. If you make this angle greater than critical angle, what happens? The light ray gets totally reflected back like this. And again when it is incident on this core cladding interface, again it gets reflected back. That means again it should be incident in such a way that this angle should be greater than critical angle. So whenever it is incident on the core cladding interface, okay, that incident angle should be greater than critical angle. Again here also, this angle, okay, it should be greater than critical angle. Again it undergoes total internal reflection. Like that the light ray gets multiple total internal reflections inside the core medium and it will not enter into the cladding medium and it gets propagated. So this is the main principle involved in the working of an optical fiber. Okay? So the main principle involved in the working of an optical fiber is total internal reflection. So when the light ray is going from denser medium to rarer medium, when angle of incidence is greater than critical angle, the light ray gets totally reflected back into the denser medium itself. It will not enter into cladding or it will not enter into rarer medium. Okay, that phenomenon is known as total internal reflection. So this is the main principle involved in the working of an optical fiber. Okay, we have to remember one thing here, the refractive index of core is slightly greater than that of refractive index of cladding. Okay, then core acts as denser medium, cladding acts as rarer medium. So this is the main principle. Next, we are going to discuss what is acceptance angle. What is acceptance angle? What is this acceptance angle? You see, just before I have considered core and cladding. The inner one is core, okay, whose refractive index is N1. This core is surrounded by cladding, whose refractive index is N2. Now the light ray is launched from air. The light ray is launched from air medium, whose refractive index is N0. Whose refractive index is N0. So this launching angle is very important. At what angle you are launching the light beam into the optical fiber plays an important role, because okay, depending upon this launching angle only, this incident angle will be there. That means the total internal reflections takes place. If you don't maintain this proper angle, if this angle is not proper, automatically there will not be any total internal reflections. So this launching angle is very important. Okay, so that means suppose the angle, maximum angle up to which you can launch. So you can launch, that means you can send the light ray. You can send the light ray in this direction or in this direction or in this direction. Okay, all the possible directions you can send the light ray. But there is always one angle, maximum angle. Okay, so if you exceed that maximum angle, what happens? The light ray, it will not be trapped in the core medium. Okay, that means the light ray will not undergo total internal reflections. The light ray will enter into cladding. Okay, so if there are no total internal reflections, it's okay, that is optical fiber, that means there will be so many losses, energy losses will be there. If energy losses are there, the purpose of optical fiber is what? If you give the light in 100% input, the output will be maximum output, like 95 to 96% output you will get. Okay, so remaining percentage will be losses. Okay, that means if you want to achieve that maximum output, this launching angle is very, very important. Okay, so there is always a maximum angle. For any optical fiber, there is always a maximum angle up to which you can launch the light beam so that it undergoes total internal reflections inside the core medium. Okay, so once you launch the light beam below that angle, okay, happily that light ray will be trapped inside the core. So the light ray will not enter into cladding. So this launching maximum angle is very, very important. Okay, that maximum angle we will call that maximum angle as a acceptance angle. Acceptance angle. That maximum angle is known as acceptance angle. Okay, so suppose if the acceptance angle is some 20 degrees, let it be. If the acceptance angle is 20 degrees, okay. If you launch the light beam at 90 degrees, 19 degrees or 18 degrees or 17 degrees, below that at 20 degrees, you can launch the light beam. Okay, even in this direction also, like this, like this, like this. But the maximum angle is how much? 20 degrees. Below that 20 degrees, okay, you can send the light ray in all these directions. But if you exceed that 20 degrees, the light ray will not undergo total internal reflection. Okay. Now all these directions, okay, all these directions, if you join, okay, you will get a cone type of structure. That cone, we will call it as, this cone, we will call it as acceptance cone. So what is this acceptance cone? Acceptance cone gives set off the directions, okay, all accepted directions. If you launch the light beam within that acceptance cone, then only the light ray will undergo total internal reflection inside the core medium. If you exceed that acceptance cone, what happens? The light ray may not undergo total internal reflection. Okay. So this cone is known as acceptance cone. The angle, okay, the angle up to which you can launch the light beam, the angle, maximum angle up to which you can launch the light beam, so that the light ray undergoes total internal reflection inside the core medium and gets propagated. Okay, that maximum angle is known as acceptance angle. That maximum angle is known as acceptance angle. You can see the definition here, the maximum angle, okay, up to which the light beam can be launched into the optical fiber so that it undergoes total internal reflection inside the fiber and propagated through it. Okay. Now a question, okay, will come like this: define acceptance angle and also derive an expression for acceptance angle. Okay, so this is very, very important question. Without this, you will not have any question paper. Okay, so this question paper is very important and repeated question. What is acceptance angle? This is the definition. And derive an expression for it. There is a small derivation for this acceptance angle and it's very easy, very important. So let us derive an expression for this acceptance angle. Okay. So for that derivation, before that derivation, we should know one law called as Snell's law. Snell's law. What is this Snell's law? Okay, same. I consider again two mediums here. Let the refractive index of first medium is N1. Let the refractive index of the second medium is N2. Okay, let the light ray is traveling from N1 to N2, medium of refractive index N1 to medium of refractive index N2. Okay, I will call this angle as theta 1. Okay, after refraction, let the angle is theta 2. Now, what is the Snell's law? Snell's law means the refractive index of the first medium, that is N1, into sine of, what is the angle made in the first medium? Theta 1. So, N1 into sine theta 1 is equal to, what is the refractive index of the second medium? N2. N2 into sine of angle made in the second medium, that is theta 2. Very simple. This is Snell's law. So, N1 refractive index of first medium into sine of angle made in the first medium, that is theta 1, is equal to refractive index of the second medium, that is N2, into sine of angle made in the second medium. This law is known as Snell's law. Now we are going to apply this Snell's law. Okay, I am going to apply this Snell's law for deriving the acceptance angle. Okay, now you can observe your 2 points are there. This is one point, point A, and point B here. Okay, your light ray is launched from which medium? Again, which medium? Air medium. Air medium. The light ray is launched from air medium. Okay, so at point A, okay, what happens here? The light ray gets refracted and it is incident on point B. At point B, what happens? It will trace, it will travel along the interface. Okay, now you can see, first let us apply Snell's law at this point. First I am going to apply the Snell's law at this point. After that, we have to apply Snell's law at this point. Okay, at 2 points, I am going to apply Snell's law here. Okay. So at point A, I am going to apply the Snell's law. At point A, I am going to apply Snell's law. At point B also, I am going to apply Snell's law. So at point A, okay, you can observe that the light is going from which medium to which medium? Air to core medium. Air to core medium. So the refractive index of air is N naught. That means refractive index of air medium is N naught into sine of what is the angle made in the air medium? Theta naught. So sine theta naught is equal to the refractive index of core medium is N1. N1 into what is the angle made in the core medium? That is theta 1. Sine of theta 1. So from here, sine theta naught is equal to N1 by N naught into sine theta 1. Let us consider this as equation 1. Okay. Now, let us apply Snell's law at this point. I am going to apply the Snell's law at point B. At point B, what happens means, point B, see, at point B, the light ray is trying to go from which medium to which medium? Core medium to cladding medium. Core medium to cladding medium. So, what is the refractive index of core medium? N1 into sine of angle made in the, okay, angle made in the core medium is what? 90. What is the angle made in the core medium? 90 minus theta 1. This angle is 90 degrees. That angle is 90 degrees. So, what is the angle made in this core medium? That is 90 minus theta 1. So, sine of 90 minus theta 1 is equal to refractive index of cladding is N2. You can observe that refractive index of cladding is N2 into what is the angle made in the cladding medium? 90 degrees. That is sine 90. Sine 90. Okay. You can see that this is N1 sine 90 minus theta, cos theta. That is cos theta 1 is equal to N2 into sine 90. Sine 90 value is 1. Sine 90 value is 1. Okay. From here, what is cos theta 1? N2 by N1. Cos theta 1 is equal to N2 by N1. Okay. But here what we want actually? Sin theta 1. We have cos theta 1. Okay. Now, sin theta 1 is equal to under root of 1 minus cos square theta 1. That is the relation between sine and cos. Okay. Now that is equal to under root of 1 minus, what is cos theta 1? Cos theta 1 is n2 by n1. Cos theta 1 is n2 by n1. That means cos square theta means what? Okay, so that means n2 square by n1 square, because you can see cos theta 1 is n2 by n1. So substituting that cos theta value. So what will we get? So sin theta 1, okay, that is equal to under root of n1 square minus n2 square, okay, by n1 square. So the denominator I am writing out of the root. Then what will happen? Under root of n1 square minus n2 square divided by n1. This is sin theta 1. Okay, actually what we want, we want sine theta naught. We got sin theta 1. Okay, so substituting that sin theta 1 in equation 1. So equation 1 implies, what is this equation 1? Sin theta naught is equal to, sin theta naught is equal to n1 by n naught, okay, n1 by n naught into sin theta 1. Sin theta 1 is what? Under root of n1 square minus n2 square by n1. So this n1 gets cancelled. Finally, sin theta naught is equal to under root of n1 square minus n2 square by n naught. Now this is the, okay, sin theta naught value. But we want a theta naught value because theta naught is known as acceptance angle. That is the acceptance angle. So theta naught is equal to sin inverse of under root of n1 square minus n2 square by, actually n naught value, n naught is what? The refractive index of air medium. But refractive index of air, generally it is taken as 1. So finally you will get this expression. So theta naught is equal, acceptance angle is equal to sin inverse of under root of n1 square minus n2 square. Okay, n1 is the refractive index of core medium, n2 is the refractive index of cladding medium. That means if you know the refractive indices of core and cladding, we can decide, we can evaluate the acceptance angle, up to which angle you can launch the light beam into the optical fiber so that it undergoes total internal reflection. Okay, if you launch the light beam exceeding that angle, what happens? The light ray will not undergo total internal reflection. So if you know the refractive indices of core and cladding, okay, you can find out the what is that acceptance angle by using this formula. Sin inverse of under root of, I am writing here, acceptance angle is equal to sin inverse of root n1 square minus n2 square. Divided by n naught is also there, but n naught value I am taking it as 1 because we are launching the light beam from air medium. Since it is launched from air medium, the refractive index of air is taken as 1. That is why this is the expression for acceptance angle. This is the expression for acceptance angle. So what is acceptance angle? The maximum angle up to which we can launch the light beam into the optical fiber so that it undergoes total internal reflection inside the core medium and gets propagated. Okay. So this is the expression for acceptance angle. Now with this acceptance angle, okay, in the examination we will also get another question. Okay, what is numerical aperture? Derive an expression for numerical aperture. So our next topic is numerical aperture. So acceptance angle we have studied. Next is numerical aperture. So what is this numerical aperture? Okay, you see it is defined as the light collecting capacity. light collecting capacity. Light collecting capacity of an optical fiber is known as numerical aperture. Okay, the light collecting capacity of an optical fiber is known as numerical aperture, and it is directly proportional to the acceptance angle. If you know acceptance angle, we can easily find a numerical aperture. What is the relation between numerical aperture and acceptance angle? Let us see. Numerical aperture, I am just writing it as NA. Numerical aperture is equal to sine of acceptance angle. Sine of acceptance angle. Okay, sine of acceptance angle is numerical aperture. That means if you know acceptance angle, when you apply sine to that angle, you will straight away you will get numerical aperture. Okay, so that means sine of, okay, what is the expression for acceptance angle? Just before only we have derived, that is sine inverse of under root of n1 square minus n2 square. So sine inverse get cancelled. Finally, you will get the numerical aperture as under root of n1 square minus n2 square. So numerical aperture is equal to what? Under root of n1 square minus n2 square. Okay, because numerical aperture is equal to sine of acceptance angle. Acceptance angle is what? Sine inverse of under root of n1 square minus n2 square. When you cancel this sine and sine inverse, you will get numerical aperture as under root of n1 square minus n2 square. n1 is the refractive index of core medium, n2 is the refractive index of cladding. Remember that n1 is slightly greater than n2. n1 is slightly greater than n2. Okay, that means in the examination, you will get a question like this. What is numerical aperture? Derive an expression for numerical aperture. First you need to derive an expression for acceptance angle, then you need to write these two steps. Then you will get the full marks. Okay, first you need to derive an expression for acceptance angle, then only you go for this numerical aperture. Directly if you write these two steps, you won't get the marks. So definition, derivation for acceptance angle, and this expression for numerical aperture. You need to write all these things. So this is what is called as numerical aperture. So with these two expressions, okay, acceptance angle and numerical aperture, regularly you will get some problems. Problems are very, very important. Okay, let us try to solve some of the important problems regarding or related to this numerical aperture and acceptance angle. So if you see the first problem, calculate the acceptance angle and numerical aperture of an optical fiber from the following data. What is data given? N1 is equal to 1.55, N2 is equal to 1.50. That means the refractive index of core, this is the refractive index of core, this is the refractive index of cladding. Okay, so you will get some easy problems only, direct substituting, formula substitution problems. Okay, so first you need to find what acceptance angle. Before that, let us find numerical aperture first. So numerical aperture, directly when you substitute the formula, that means under root of n1 square minus n2 square, that is under root of 1.55 square minus 1.50 square. Okay, so directly if you calculate this value, you will get it as numerical aperture as 0.39. This is the numerical aperture with this two refractive indices. Okay, when you have numerical aperture, you can easily find acceptance angle. How to find this acceptance angle? Acceptance angle, already you know the expression, theta naught is equal to sine inverse of under root of n1 square minus n2 square. But already you know the value of root n1 square minus n2 square. Okay, what is its value? Sine inverse of 0.39. Okay, so what would be the value here? 22.98 degrees. This is the value of acceptance angle. Okay, so this is numerical aperture. Okay, how much you got? Numerical aperture you got it as 0.39, acceptance angle you got it as 22.98 degrees. Okay, so very easy problems only you will get. Okay, let us try to solve the next problem. What is that? A fiber cable has an acceptance angle of how much? 30 degrees and a core index of refraction of 1.4. Okay, that means what are the given things here? First write down the given things. Okay, acceptance angle is equal to 30 degrees and core index of refraction, that means refractive index of core is given as 1.4. Now calculate the refractive index of cladding. We need to find out N2. You need to find out N2. So how to find it out? Okay, how to find it out here? Direct we have one formula. Okay, we have formula. What is the formula here? Sin theta naught is equal to root n1 square minus n2 square. Okay, so substitute here. Sin 30 is equal to root 1.4 square minus n2 square. So sin 30 is 1 by 2, okay, root over 1.4 square minus n2 square. So by squaring on both sides, when you square on both sides, what will you get? 1 by 4 is equal to 1.4 square minus n2 square. Okay, so then n2 is equal to, okay, root 1.4 square minus 1 by 4. If you calculate this, okay, what value you will get is n2 is equal to 1.30. Like this, you can solve this problem. Acceptance angle data is given and refractive index, what is that? Refractive index of core is given. Okay, you need to find out the refractive index of cladding. So directly use this expression and get the value of N2. Get the value of N2. Okay, and you have another problem also where you need to find out, that means a silicon optical fiber with a core diameter large enough has a core refractive index of 1.50. That means N1 is 1.5 and a cladding refractive index is how much? 1.47. What we have to determine the critical angle. Critical angle you need to find out. Okay, and also you need to find out the numerical aperture of the optical fiber. Okay, so critical angle, there is a formula for finding out the critical angle. What is the formula for critical angle is, critical angle is given by sin inverse of N2 by N1. So what is the expression for critical angle? Critical angle is given by what? Sin inverse of N2 by N1. Okay, so sin inverse of N2 1.47 by N1 1.5. So what is the answer for this critical angle? You will get 78.52 degrees. 78. This is the answer for critical angle. And also you need to find out the numerical aperture also. Okay, So let us find out. N1 is given as how much? 1.5. N2 is given as how much? 1.47. Okay, you need to find numerical aperture. So directly you can substitute in this expression n1 square minus n2 square, that is equal to root 1.5 square minus 1.47 square. Okay, the answer would be 0.298. This is the answer. So here two bits are asked. You need to find out the critical angle as well as you need to find out the numerical aperture. Critical angle expression is sine inverse of n2 by n1, and the numerical aperture is sine, what is that? Under root of n1 square minus n2 square. n1 is the refractive index of core, n2 is the refractive index of cladding. Okay, these are the problems related to acceptance angle, numerical aperture and critical angle. These are the important problems. Next, we are going to discuss attenuation. What is attenuation? While the light ray, you will send the information to the optical fiber in the form of light energy. Okay, if you want to transmit any information, okay, to a longer distance, actually optical fibers are mainly used to carry the information to very long distance. Okay, because if you use normal cables, what happens? Power losses will be high. So copper cables, if you consider, where electronic signals are used, what happens here? Electrical signals are used. What happens? So power losses will be high. So instead of that copper cables, we prefer optical fiber cables. Optical fiber cable consists of lot of optical fiber wires, bunches of optical fiber wires, very thin. Optical fiber is nothing but a very thin and flexible medium. Okay, so this optical fiber, while the light energy is transmitting through the optical fiber, what happens? There may be some energy losses during the transmission. Okay, there may be some energy losses during the transmission of the signal. That energy loss during the transmission of the signal in the optical fiber is known as attenuation. Okay, you can see that attenuation is defined as the reduction in the signal strength. Okay, the signal strength gets reduced. The signal strength gets reduced when it is transmitted through the optical fiber. So when the signal is transmitted through the optical fiber, there may be some reduction in the strength of the signal. This reduction in the strength of the signal is known as attenuation. This is the definition of attenuation. So you will get sometimes explain attenuation in the optical fibers. Okay, what is attenuation in short answer? Write short notes on attenuation. So in various ways this question will be asked. So this definition is very, very important. Now attenuation loss is generally measured in terms of which unit? Decibel, dB. Decibel, it is the logarithmic unit. Decibel is the unit for attenuation. So what is the unit for attenuation? Decibel. Decibel is the unit for attenuation. So what is the formula? The decibel, the decibel loss of optical power in a fiber is given by, that means what is the expression for this? It is minus 10 logarithm of P out by P in. What is this P out? P out is the power emerging out of the fiber, that means output power. Okay, output power. P in is the power launched into the optical fiber. P in is the power launched into the optical fiber, and L, capital L, is the length of the cable. L is the length of the cable. So this formula is very important. Minus 10 logarithm of, okay, keep minus logarithm of So this is the formula that we are going to do. What is this? Minus 10 logarithm of output power, P out by P in. So P out is the power emerging out of the fiber, P in is power launched into the fiber, and L is the length of the cable. Okay. Now, while transmitting the signals through the optical fiber, some energy will be lost due to few reasons. That means how many types of energy losses will be there? How many types of energy losses? That means attenuation, okay, it is divided into two. That means two losses will be there. That is transmission loss. You have transmission loss. You can see here. This is called transmission loss. Transmission loss, and you have distortion losses. Two types of losses you have. What is that? Transmission losses and distortion losses. Okay. You see, again these transmission losses. First, transmission losses. Transmission losses are the mechanism of attenuation during the transmission. Again, these transmission losses are divided into, two categories. Okay. The first one is absorption losses. The second one is scattering losses. What is the first one? Absorption losses. The second one is scattering losses. First, let us see. So that means whenever the signal is transmitted through the optical fiber, you may have any loss. Okay, whether it is transmission loss or distortion loss. Again, this transmission loss is divided into two: absorption loss and scattering loss. First one is absorption losses. That means whenever the signal is transmitting, whenever the signal is transmitted through the optical fiber, whenever the light is incident on the optical fiber, what happens means optical fiber is nothing but core medium. That core is made up of glass material. So that glass material may absorb some of the wavelengths of the light. Okay. So that leads to absorption losses. So whenever light is incident on the core medium, core is made up of what? Glass material. So that glass can absorb some of the light energy. This energy loss is known as, what is that? Absorption loss. Okay. So absorption is a characteristic possessed by all materials. Every material in universe absorb suitable wavelengths as they are incident or passed through the material. Okay. So that core medium, it is made up of glass material, it will absorb some of the light energy. Such type of losses are known as absorption losses. You can see that. And sometimes in the core medium, there may be some impurities. Impurities may be absorbed, or impurities may be observed in the core medium. So these impurities also may absorb some of the light energy. Okay. The impurities present in the core medium also may absorb some of the light energy. So that energy loss, because of the absorption of the energy by the impurities, is also considered as absorption losses. Okay. So the energy absorbed by the impurities is also known as energy absorption loss. Okay. While during the fabrication of the glass material, there are some impurities to be added to the glass material in order to improve the properties of the glass material. So those impurities present in the core medium, because core is made up of glass material, the glass material also may consist of some impurities. Those impurities may absorb the energy. That also leads to energy loss. Such type of losses are known as absorption losses. The next one is scattering losses. Okay. So scattering losses. Scattering losses, what happens? In scattering losses, you can see that the core medium of the fiber is made of glass or silica. In the passage of optical signals in the core medium, if crystal defects, you can see that crystal defects. If any crystal defect is observed, in intermediate you might have studied about the defects. Okay. If you have a regular arrangement of atoms, if any extra atom is added to the regular arrangement of atoms, that is considered as a defect. Or if suppose any atom is missing, if any atom is missing in the regular site, that is also considered as one of the defects. So if such type of defects are present in the core material, because core material it is made up of glass material, in the glass material, in the regular arrangement of atoms, sometimes there may be a chance of missing atoms or extra atoms. These missing atoms or extra atoms are also considered as defects. If such type of defects are present in the core material, okay, that defects also, because of that defects also, what happens, the light will not go, okay, in the regular direction. The direction will be deviated. The total internal reflection will be deviated, will be discontinued. Okay, the total internal reflection will not take place. What happens, some of the energy will go into cladding, some of the energy will go in the backward direction, you can see like this. So the energy will be scattered in different directions. Okay, actually the light has to go in this path, but because of what happens there, density fluctuations. So that means regular arrangement of atoms is not there. Maybe more atoms or no atoms. Because of that fluctuations, what happens there? Scattering of light takes place. Scattering of light takes place. Such type of energy losses. Due to the scattering, some energy will be thrown into cladding. So cladding material will absorb some energy. Some energy will be, okay, it will be going in one direction. So in different directions, the energy will be scattered. So because of this scattering, some energy losses will be there. Such type of losses are known as scattering losses. Next, distortion losses. Distortion losses. If you send the input signal, okay, if you send the input signal, what happens means output signal also should be same as input signal. Output signal also should be same as input signal. Okay, if there is any difference between output signal and input signal, we say that the signal is distorted. Okay, when a pulse is launched at one end of the fiber and collected at the other end of the fiber, then what happens? The shape and size of the pulses should not be changed. There should not be any change in the output pulse as compared with the input pulse. Okay, if there is any change, okay, if there is any change in the output pulse, okay, compared with input pulse, we say that the signal is distorted. The signal is distorted. Okay, so this distortion, okay, we say the distortion of signals in optical fiber is an undesired feature. Okay, and if the output pulse is not the same as the input pulse, then it is said that the pulse is distorted. The pulse is distorted. Okay. This distortion mainly takes place. What is the reason for the distortion? Because of some of the impurities, because of some of the defects present in the material, you may have such distortions. So distortion may take place because of some imperfections, or imperfections means defects. Imperfections are nothing but defects and impurities, and what is that? Some doping concentrations, some of the impurities, doping concentrations. So because of this, the distortion may take place. You can see that, you can see the variation here. This is the input pulse. This is the input pulse. You see the output pulse, that's overlapping of output pulse. Output pulse is overlapped. Okay, output pulse is entirely different from input pulse regarding in terms of shape and size and strength. Okay, there is a difference between this output pulse and the input pulse. This difference between the output pulse and input pulse is known as distortion. That difference is known as distortion. Okay, and you also have bending losses. The next loss is bending loss. That means if the fiber is straight, you can see here, if the fiber is straight, total internal reflection takes place continuously. Total internal reflection takes place. Okay, but when the fiber is bent, what happens? The angle may change. The angle at which the light is incident here, you can see here, this theta. Okay, as we have discussed that theta plays an important role at which angle that light is incident. okay, that will decide whether the total internal reflection takes place or not. If the total internal reflection does not take place, so okay, power losses will be high, okay, because the output power is different from input power. Power losses will be high. So what happens here, when the fiber is bent, we can observe that there will be some, okay, angle, the direction of the light ray also changes because of the change in the angle. Okay, there will not be, sometimes the total internal reflection may not take place. The total internal reflection, because of this bends, micro bending, because of that small bendings, the total internal reflection may not take place. Because of that, what happens? Power losses will be there. Then what happens? The output power is different from input power. Okay, so this is mainly due to bending losses. Okay, so these are the different losses in optical fiber. We have transmission losses and distortion losses. Okay, and again transmission losses, we have absorption losses, scattering losses, okay, and bending losses. Okay, right. Next, the applications of optical fiber. So where do we use optical fiber in our daily life? Okay, one thing is in communication system. When you send the signal, light signal, okay, through the optical fiber, what happens? You can transmit the information to that means even up to hundreds of kilometers without much power losses. Okay, that's why these optical fibers are immensely used in communication system. You can see that in recent years, optical fibers are being used instead of copper cables, where the light signals replace what? Electrical signals. Okay, in case of copper cables, we used to use electrical signals, but in optical fibers, we use light signals. Okay, you can see that the input data, it is transmitted to transmitter circuit. From here, light source, it is through optical fiber cable, it is going to detector. From detector to some another circuit will be there, that is receiver circuit. From there you will get output data. So input data, okay, through transmitter circuit, okay, through a light source, it is mixed with light source, through the optical cables it is sent to the detector, and from there receiver circuit, from there you will get the output. Okay, so this is the application in communication system. In medical field also we use these optical fibers. Where do we use this optical fiber? Optical fibers are used in okay, endoscopy. Optical fibers are used in endoscopy. In cardiology also we use these optical fibers. In ophthalmology, that means in the case of eye treatments, and in case of treatment of cancer also we use these optical fibers. Okay, you can see that if a patient is suffering from stomach pain, okay, so to scan the internal parts of the stomach, doctors generally they insert one small optical fiber wire inside the stomach, and they will scan the internal parts of the stomach, and it is connected to a monitor here. So in the monitor they will observe, okay, what is the problem inside the stomach. They can detect the problems. So the fiber that is inserted into the stomach is optical fiber. So a laser light will be sent into the stomach, and that will be that laser light will go and will get reflected, and it again get that reflected light will is connected to a monitor. In the monitor they will observe that all the parts of the stomach, and they will detect the problems. In the lighting and decorations also, nowadays, okay, the people are going for different lighting and decorations. Okay, for celebrations, during celebrations time, so they are very crazy about lightnings. Okay, so in the lightnings we use this optical fibers only. Okay, you can see that, and it is very easy. Optical fiber cables, they provide easy, economical and attractive solution to this lightning projects. You can see that the colorful lightning decorations, okay, it is possible with this very small optical fiber wires. And also mechanical inspections. That means wherever, okay, if you want to detect the problem, suppose in the big pipes where you cannot go and you cannot see what is the problem inside the pipes, okay, in the different machines where we cannot detect, we cannot enter manually. So in such cases we will insert the pipes and we can know the problems. Okay, hard to reach places, you can see that optic cables are widely used in the inspection of hard to reach places, the places where you cannot reach. Okay, in such cases we use this optical fibers. Some such applications are on-site inspections for engineers who are working. Okay, if they want to know what is the problem, okay, then they can detect by sending this optical fibers, and also inspection of pipes for plumbers. So next, automotive industry. In automotive industry also optical fiber cables are used. Okay, they play an important role in the lightning and safety features of present day automobiles. Now in present day automobiles, lightning also plays an important role in the interior of the vehicles or in the exterior of the vehicles. Okay, in the interior or exterior of the vehicles, what happens, the people are crazy about the lightning and decorations. So in such cases a small optical fiber wires are also used, you can see here. Okay, so in the cars, okay, we use this lightnings. Okay, so these are the different applications. These are the different applications of optical fibers. Okay, so optical fibers are used where, even in communication system, optical fibers are used in medical field, optical fibers are used in medical, in endoscopy, ophthalmology, treatment of heart treatment or treatment of cancer. Okay, and optical fibers are also used in automotive industry, okay, in lighting and decorations. So these are the different applications of optical fibers. So with this I am going to, okay, wind up this session. So I hope this video will be useful for the students who are going to write the examination, okay, in the coming days, because this optical fiber concept is very important and it is scoring subject. So thank you for giving this opportunity.